Hello everyone, welcome to this special Friday Quantum Space-Time Seminar. Today we are very happy to have Caron Huot from McGill University, and he's going to tell us about gravity, post from ultraviolet. Over to you.
Hello everyone, it's a pleasure to be with you virtually. Can you see my slides?
Yes. Yes.
Thank you. Yeah. So we were talking about some series of papers. Of course, yeah, try to be focused on the last two ones in order to make for a concise story. The work is really about dispersion relations and how to use them to constrain low energy theories. But like if I say it's going to be a talk in dispersion relations in the title, nobody's going to show up. So that's why I put that with gravity. Personally, like my background, I'm very interested in the strong force and other applications of this. But as will be clear, it will become clear throughout the talk, it seems that this tool, dispersion relations, is somehow really made to tell us something about gravity. So looking at that now. The story I'm going to tell builds on the work of many others. I will not go through, and I'm not even including a complete list, but I will not be very systematic with reference during the talk. But keep in mind that's it's a big field. Okay. So I thought one way to start, and feel free to interrupt at any time. So I thought I'd like to start with since we're going to explore constraints from causality, I thought it'd be fun to start with just a simple question like, what has causality done for you recently? Like, as a principle in physics, it's been an extremely successful. It's been successful at explaining various aspects of the world. Like, let me just list a few examples. So the basic level, it explains why we have waves and fields. And that's such a nice argument that I have to spend I have to review it. It's like a classic argument is that if you have so causality says that information should not travel faster than light. Loosely, that's the idea that it will mean in this talk. So if you have some particle at the point A and you displace it at some time t, you kick it, the information that this has moved is going to change the force on some other object B, but this force should only change after the time it takes for light to travel. But since the force on B changes, then force is momentum, so something has to carry energy and momentum from A to B, and that thing is why we have electromagnetic waves. And that is why Einstein could predict gravity waves, essentially even before he had the equations to describe them. They had to exist. And in the quantum theory, well, if energy comes in discrete units, it explains why all forces are mediated by particles. And when you go deeper into the quantum theory, you learn that the idea that measurements at A and B commute with each other explains why we need to have antiparticles. And there's also a cool fact that will come later in this talk that it explains why gravity is to be attractive. Let's just explain that it has to exist and make waves. Not less exist, but has to make waves. Why it has to be attractive. So, well, after this series of success, I've set the bar so high that I can only disappoint. But what I'm going to talk about today is one more sort of something I view as an interesting consequence of causality, is that it gives an explanation for why effective theories have to work. So that's going to be the main topic today. And what I mean by that is that, so effective theory is going to refer loosely to the idea that if you describe a system that you know all the degrees of freedom up to a scale m, you expect that this system at low energy is going to be the effect of the scale m is going to describe by some derivative expansion, where higher derivative are suppressed by by higher powers of the short distance or the quantum wavelength of the new physics. That's an expectation, we believe, and we can verify it in all examples where we have UV physics and we figure it out. And with causality, you kind of get what I'm gonna argue is that we get this feature as a consequence of causality without having to assume that the UV completion is even anything remotely similar to a local field theory that we can integrate it out. That's very generic consequence. So that's it. So we're going to explore consequences of causality. It's not that causality is a religion, right? It's not because it's so successful that it has to be exactly true. I don't know that it's exactly true. It's important to test it experimentally. It's also theoretically not even so clear what causality exactly means for bulk observers in the gravitational theory, like we are. So the spirit here is just to explore, and it's just somehow the beginning of some exploration. What can we prove directly using ideas of using this, trying to make quantitative predictions that test causality. So the main tool we use, yeah. So that's the spirit. The tool we use is dispersion relations, and again I will start from, before moving on, describe the classic one from Kramer's Crony in the 20s, and explain at the same time how we use it. So what they wrote in this old formula, they have a formula for the dispersion of light. So when light goes through a medium, the phase velocity of light is changed. So that would be a diffractive index, kilo omega. And you can say, so what they wrote is that it's basically the speed of light plus the correction. And what they understood is that the correction to the phase velocity are controlled by the weight that light can absorb. Sorry, the way that the material can absorb light. So that's the imaginary part of this diffractive index, also known as the absorptive part. Okay. That's just a formula. It's kind of cool that these things are related, but it's nice to make a plot. So the basic idea here is that we're going to plot as a function of frequency the phase velocity, which is omega over k. That's a phase velocity. I'm going to plot this as a function of frequency. So in vacuum, you just have like the speed of light. Now we're going to imagine that there's some absorption peak in your spectrum. So you have some imaginary part that has some bump. And then we feed it into this formula, we get something. And the important thing about what's going to be important in this talk is the sign. And the sign of what you get looks like this. So it's negative below, then it goes 0, so it's a odd function, and it looks kind of like this. Okay. And the sign is kind of, well, it's forcing you by the formula, but usually also absorption comes with positive sign. So you have this generic shape. And what this shape tells you is that the effect of ultraviolet physics is only to slow you down in the infrared. So I'm going to abbreviate it as a slogan: UV can only slow you down. In the context of optics, you can take this literally, like the reason that visible light moves more slowly in air than in vacuum is because you have air molecules have all these absorption bands in the ultraviolet. So ultraviolet is slowing light. But in this talk, the idea is that UV is going to stand for some short distance physics, unknown short distance physics above some EFT cutoff, and us are going to be some low energy observable at an EFT below that scale. So so this general tool of dispersion relation relate things that can occur at high energies to things that you can measure at low energies. And the sign is kind of universal. It can slow you down, but never speed you up. Okay. This does not mean, right, notice that it's possible to have a phase velocity faster than light, but only if you're above a bump. But the effect of the UV and the IR always has a specific sign. That's the point. So the plan of this talk is going to review S-matrix dispersion relations. And the last paper 2 weeks ago was really about how do we justify using these in theories with gravity. And at least in the context of ADS-CFT, we believe we have some clear justification. So the first part of the talk will be about this. And after that, I will tell you, like, what do we actually do with these dispersion relations? How do we use positivity above a cutoff to prove bounds about what's below the cutoff? So that's the plan of the talk. Okay. So the rest of the talk is pre-written. Yeah. So okay, we're going to look at the simplest setup, which is 2-to-2 scattering and flat space. Matrix, and the ingredients that enter Kramers-Kronig-like relations. I'm not going to review the proof. It's a familiar proof from textbooks. Basically, you need to look at the complex energy plane, or Mannestam S plane, which is like linear in the energy of one particle. And you have to use two ideas. You have to use that it's analytic in the upper half plane, and you have to use some boundedness property. The general template of the argument is that you want to deform contour integration and somehow be able to drop some large arcs infinity. So you need these two properties. And these two ingredients together give you dispersion relations. This does not come, so these principles are related to causality and unitarity in some clear way. It's going to be useful to have in mind what is kind of like the classic heuristic picture for why this works. Can I tell you the rough picture, which I think is compelling, and then after that I will tell you the ways that's incomplete. Okay. But the rough argument, if I try to phrase it as clearly as possible, is the following. So one starts with an object which has a nice time domain structure. So you take the retarded commutator in scattering state. So 2 and 4 are particles moving to the left. And you take commutator between 1 and 3, and this commutator vanishes outside the future light cone. Okay. And then what you do is you just take this object and you Fourier transform it. And this support property means that it's going to be analytic at high frequencies. And this is just a simple statement about Fourier transform. Like if you integrate over time from 0 to infinity of a Fourier phase and some function of time, you're going to get something that's analytic in the upper half plane, because adding an imaginary part to omega just makes the integral more convergent. So you get analyticity is clearly related to causality and the fact that things vanish outside the light cone. And the other thing you need is that you can bound the correlator, and roughly this comes from looking at two-point function. So you know that scattering is always like you always write scattering amplitude as a 1 plus a connected part, but unitarity basically loosely tells you that the connected part can never overwhelm the disconnected part for a normalizable wave function. So the disconnected part dominates everything, and that gives you some boundedness properties. Or mathematically, this tells you like how many subtractions you have to do in this dispersion relations. Okay? And using this argument, you can come up with a precise number for how many subtractions you have. Okay? These are people who wrote paper on dispersion relation in the 40s. If people can name them, I finish my slide. That's a challenge to the audience. Before I move on to the subtleties, let me explain what's great about this picture. Okay, so this picture not only explains dispersion relation, it's really an explanation for crossing symmetry. And And the point is that you might have stuff that causality is a statement that particles sent from 3 will not reach 1 faster than light, but this is not true. You can have correlations between 3 and 1, and these correlations can be affected by going from 2 to 4, from the other particle you're going across. The statement of causality is that the commutator here vanishes, which means that the amplitude for a particle going from 1 to 3 is equal to the amplitude for antiparticle going the other way. This is what crossing is really about. And yeah, so that was also integral in this picture. You can't have like dispersion relation if you don't have in particular crossing that relates an amplitude to a complex conjugate amplitude by some large paths in the upper half plane. So crossing is integral to the argument. And
this crossing argument.
Yeah, sorry. I usually use the word crossing for S matrices. So does this picture tell you that S matrices obey crossing symmetry?
At least a 2 to 2 S matrix, yeah. I'm not sure how to use this argument actually for higher point. But yeah, this picture, yeah, this picture to me is how I understand crossing, yeah.
And how do you relate this to the S matrix, given that the S matrix is is a causal configuration?
Yeah, that's my next slide. Yeah. Yeah, the issue you're anticipating is that the region where the commutator vanishes doesn't overlap with the region that we usually use in fixed angle scattering. I think is that the issue you're worrying about?
Yes, yes. I in particular.
You're right to worry about that.
Okay, thank you.
Yeah, but yeah, modulo this caveat, I think this is basically the picture for why something like crossing has to be true. Okay. And the other thing I want to stress here is that yeah, going back to fixed angle scattering, if you think about causality in fixed angle scattering, it's actually not constraining at all, because in fixed angle, if you're going to measure a particle at point 1 here, this point 1 here is always deep in the future light cone of some initial point 3. Right? So if you do fixed angle scattering, you're so deep inside the light cone that the statement that space-like commutators vanish is completely useless to you. Okay, so the place where causality is constraining is in the forward direction, where there's a chance that you leak out, and that is why in all this discussion of causality constraint on S matrices, you always focus on the rigid limit, which is high energy. Well, in this plane here was like large energy with either fixed impact parameter or fixed momentum transfer. Okay, because you have to be doing forward scattering.
Sorry, Simon, I mean, for fixed angle, why can't you worry about the particle leaking out of the light cone, just on that direction? I mean, it doesn't have to be.
Yeah, well,
yeah.
So this dark light cone here is a bit of a construction, because it's a light cone that the light cone that I drew is something that emanates from an imaginary scattering point in the middle. But if you're scattering objects, you don't really know that they have to scatter at a point, and they can miss each other and so on. So the thing that gives you this commutator argument, that's really about whether operator 3 can send a signal to operator 1. What really matters is the light cone that emanates from operator 3.
Yes, thank you.
Yeah, so that is the point. So yeah, okay. So that's the basic picture, and like this. Somehow this picture works beautifully, right? Crossing symmetry and the fact that particles and antiparticles and so on is beautifully verified in the world. But yeah, now I have to come to the important details that are hidden here. So the first one is that the domain of analyticity that's implied by causality actually doesn't intersect with what we use in the LSZ reduction formula, which is the fixed angle scattering kinematics. That difficulty has a technical solution in axiomatic field theory, but I think it's fair to say that if we're going to apply this argument to theories without a gap, theories that have gravity, theories that don't satisfy the axioms, it would be nice to have other other arguments. The other thing that
the technical solution is that you can analytically continue.
No, it's a bit deeper. Well, I mean, I actually don't understand the full details of the proof. You have to prove that there's a bigger analyticity domain, and the proof used very much things like mass gaps and not the details. And also the end result of the proof is that they were able to show that you have analyticity at large enough S for some T, but they don't actually tell you like how large S has to be, and there's a lot of details that are not completely, you might want to improve on.
So this is talking about the proof of boundedness. Sorry, the proof of this thing crossing.
Yeah. Okay. Yeah, I mean, there are some people in the room here, I think, who understand this much better than me, but I think there would be agreement that that there's even on something as basic as crossing, there's still more to understand. And the other thing is that well, when you think about the boundedness ideas and like how many subtractions you need, well, the rigorous theorems from the old days, they require a mass gap, like the things that Martin proved. If you don't have a mass gap, I think you can cook up arguments, and that people have always hesitated to publish them, and I think there's a reason is that the arguments are tricky because there's an awkward mix of, and you have to use some mix of impact parameter physics and fixed momentum physics. It's very subtle. So loosely speaking, the idea of why things should be bounded is that you can write the scattering amplitude. So this is the one we used to in momentum space. You can write it as a Fourier transform of something in impact parameter space. And the thing in impact parameter space is morally bounded because it's like normalizable wave packets. So you can morally bound it. However, in order to bound things in the upper half plane, you need things with nice analytic properties, and this does not have nice analytic properties. So the problem on the right is that it's not so well defined unless you use arbitrarily large momentum. And the thing on the left is the problem that you cannot bound it without using arbitrarily large impact parameter. so you're really stuck between a rock and a hard place. So to really bound this, you have to estimate, okay, there's a power of S, this is bounded, but you have to estimate this Fourier transform, and that's an interesting project and thing which involves physics like black hole strings. In theory with gravity, interesting things do happen at large impact parameters. So estimating this is not completely trivial. But you can make physical arguments, and I've done in the past. But yeah, go ahead.
Yeah, sorry, Simon. Could you say a little more what you mean by morally bounded? Could you give us the moral of this?
Yeah, well, if it were, okay, I'm going to avoid this. Yeah, if I mean morally, because it's not completely well defined. Because if you if you define, it depends how you define M. You can define it from partial waves. Then it's rigorously bounded, but it doesn't have nice analytic properties. Or you can define M from this formula. But then the problem is that the Fourier transform requires you to use the inverse transform requires you to use infinite momentum on the left. And that takes you into a deeply unphysical region. So yeah, it depends how you define it, but yeah, you could define it so that it's exactly bounded, but then it's not analytic. So it's hard to make arguments about it's complex behavior. But what we're going to do today is we're going to effectively avoid those two issues. So we're not going to prove momentum space dispersions. We're going to prove something slightly weaker. So the weaker thing is the following. Let's consider a test function.
Sorry, Sam, sorry to interrupt, but just to make sure I'm understanding. When you say, if you define it using partial waves, you say you trade B for a J, and this is just the partial wave amplitude, and that is bounded by unitarity.
Exactly, yeah.
Okay,
yeah.
Thank you.
Yeah, exactly, yeah. So you could use M, S, J, and that's bounded, but it's not analytic. So if you want to apply things like bound of chaos and so on that thing, it's not going to work. So what we do today is we're not basically going to weasel our way of these problems by using suitable test functions. So it's actually the idea is actually very simple, and really the idea is to be as close as possible to this physical picture on the left there of why causality why dispersion relation should work. So our test function will have compact support in momentum space, and they're going to have fast power law decay in B. So the compact support in P, essentially they are supported in they're going to be physically, we're thinking about applying this to effective theory. So we're going to thinking about doing measurement with impact momentum transfer less than the cutoff and energy somehow higher than the cutoff. So they have compact support in B, sorry, in momentum, and they have fast power law decay in B. And basically, right, these things avoid these problems. The compact support is going to give you analyticity easily because at energy is larger than the momentum, you are in the physical region, and it's going to be nice. And the fast decay is going to buy you make things very easy to bound, because the Fourier transform, you can basically ignore the factor of you can basically ignore the Fourier transform in doing estimates. Okay. So we're going to focus on test function with these two properties. So in the context of ADS CFT, we're going to construct CFT sum rules that in the flat space limit that are rigorously valid in any CFT, but in the flat space limit of ADS give you exactly weighted moments of the imaginary part of the scattering amplitude. And these moments have the following properties that they have momentum less than the cutoff and energy above the cutoff. So you see that. And essentially essentially the message that you could just declare that the smeared amplitude are bounded, but don't grow faster than S. Like, so there's an S in this formula. So M over S is bounded. That's basically the statement. So that's the statement we're going to use. And then I'm going to show that this statement is actually interesting and useful, and you can prove interesting bounds using this statement. So we expect that more is true. And for example, in many talks, I use, for example, the idea that M over S squared go to 0. That's often used. And there are other things. What we're going to use in some sense is stronger for the energy dependence, but it's weaker because we have to smear in momentum. Okay, it's a different thing. But by doing that, we avoid all of these interesting but subtle physics about large impact parameters. Okay? And I think it makes the story very much more straightforward.
How do you keep control over the analytic structure after doing this integral over P?
Yes. Yeah. Okay. Hopefully that will be clear. But loosely speaking, the fact that we remain in the fact that we only have to evaluate the imaginary part in the physical region would be the key. It's but in the complex plane, it's in the CFT calculation, loosely speaking, there's a saddle point that you can track.
Mm-hmm. And in the integral is 0 to M, where M is what?
Yeah. So well, M is arbitrary, but it points as the same in both integrals. So in application, we're going to think of it as some separating scale. So there's we care about the imaginary part above the cutoff, and then we're going to do contour integrals that look like this. So in the complex frequency space, in the complex energy plane, we're going to do contour integral that have that start at S equal M square, that end at U equal M square, and that they go at the cutoff. We think of the integral as like going on an arc that's at the EFT cutoff. So there's a UV contribution and there's a IR contribution. That's the contour you should have in mind. So we're going to show that this contour can be realized in ADS CFT.
And this boundedness property that you write in point 1, this is before doing the S integral, right? Just doing the T integral.
Exactly. Exactly. Yeah. So it implies that if you do any number of subtraction more than 1, would give you valid sum rules where you can ignore arcs. Mm-hmm. Yeah. So the correct number of subtraction is any number bigger than 1.
So in flat space, this sounds a little like you're saying that the S matrix is bounded by S at fixed T.
Not at fixed T, after smearing in T, yeah. Okay.
So I was going to ask, the Froissart bound is a little weaker than that. because
No,
it has
it's
log s.
weaker. Yeah, exactly. It's weaker, but it has a fixed t.
And these two things are consistent. So if you take this
They're
bound, and then
they're consistent because we have fast decay and impact parameter.
Okay. Okay, thank you.
Yeah, so the way that the forces are bound, the way you get an amplitude that grows logarithmically is that the size of the object grows logarithmically with energy. But this fast decay just makes you not care about that effect.
Okay.
That's the trick. Yeah, so we do get something that's effectively stronger than the forces are bound when focusing on these objects. Yeah. So from here,
sorry, Simon, so you don't use the Frost bound for the dispersion relation because you want to apply this for massless particles. Is that
correct? Yeah. So I mean, you might think that something similar is valid, but it can be generalized. But yeah, the Frost the Martin's proof, the Frost bound does not apply if you don't have a mass gap.
Thanks.
And you might not, people have questioned whether you can really use these things in gravitational theory, and I think there are legitimate concerns.
Right, but do we know of theories, Simon, which saturate the Frost bound, where the S matrix at fixed t grows faster than S?
At fixed t?
Grows faster than S.
Asymptotically,
yes.
Well, no, I think in string theory it does, and I'm not just talking about tree level, but I think in non-persistent string theory, I think it goes like, I think this behavior of that you get at tree level string theory, that's S to 2 plus alpha prime t, that only converge, that's only less than 2 for negative t. I believe it's actually true in when you include loops and all that. And, at very large. I think this behavior is there in string theory.
You're saying that we take black holes into account and so on, and you'll still get this behavior?
Yeah, you get this behavior basically because of tidal excitations outside the black hole.
Because of tidal what? Sorry, please.
Yeah, tidal dissociation of strings outside the black hole radius will give you something that.
So this like amplitude is not, the radio amplitude is not dominated by things far away from the black hole, like when Etienne was telling us.
Yeah, exactly. It's dominated by things far away, but it actually gives you this behavior in the fourth element. It's surprising.
Including with an alpha prime.
Yeah.
Oh. It's
surprising. We can discuss more, but
okay, thank you.
I mean, there's really cool physics in this. So don't get me wrong. We're going to look at we're going to ask physical questions where this physics is completely irrelevant. That doesn't mean this physics is not interesting. Okay?
Sorry, could you also this for string theory? Do you have a reference for this? What you just said?
No, so maybe I'm wrong.
Yeah. No, I'm curious. I wanted to read more about it. Yeah.
Yeah, I think, I mean, there's a classic series of papers by Veneziano and friends in the 90s. It's very likely that it's in there, but I will not be able to tell you which paper.
Thanks.
Maybe someone in the audience. So, okay, yeah. So from at this point in the talk, I can do two things. I honestly think it makes more sense if I tell you what we do with these sum rules because they're jumping into a proof before you saw the goal of the object may not be very productive. So I'm going to tell you like why these sum rules are actually useful and interesting. And I think that's where the physics is. So, but ultimately, the reason we can, before I describe, I mean, I would only go quickly at the end on the CFT construction. But ultimately, like the reason our CFT construction works is because we identify a sensible flat space target. It's not because of some CFT magic. That's why it's going to work. So yeah, so let's apply this idea to bound effective theories of single scalar. And yeah, I would go straight to the more recent developments and skip the history. So our assumptions are the following. We assume that below some cutoff scale, the theory is we have some weakly coupled effective theory that we're going to treat at tree level. But above the cutoff, we're going to assume that the theory remains causal and unitary. We just don't know what degrees of freedom there are in it. There could be more degrees of freedom. They could be strongly interacting. Complicated things can happen. Doesn't have to be a local field theory, as long as it satisfies the axioms that they don't allow you to send signal faster than light and unitarity. That's how we assume. So the low energy So the first step is define what we try to constrain. So at low energies, the amplitude looks like this. So if we have gravity, there's a, so this first term is like graviton exchange. Then you could have some 3-point interaction. You can have some pi4 term. And then there's a series of higher derivative corrections. Okay. And our goal roughly is going to say things about these coefficients. And they're easy to enumerate. They're just symmetrical polynomials in STU. Sharp polynomials in these two things. And this is the most general 2-to-2 amplitude. The way we're going to constrain this is using this sort of sum rule. As I said, basically the result from this EFT conclusion is that anything with more than one subtraction converge. So that's an integral with 2 subtractions. So there's 2 powers of S at large S. One subtraction doesn't buy you anything if you have, odd number of subtractions when you have identical particles trivially vanish by antisymmetry between S and U channels. So really 2 subtraction is what we actually do here in this example. So the basic idea is we do this contour integral that I just described earlier. And this contour relates physics at the EFT with the imaginary part on the UV. Okay, that's what I wrote here. Okay, so we got some contour integral in the EFT. Something you can compute is expressed in terms of an infinite sum. So the only thing we know about the UV is that from its partial wave expansion, its imaginary part is a sum of Lejeune polynomials with positive coefficients. That's all we know about the UV. We're not going to use any other properties of this partial wave coefficient. Notice that the amplitude is not positive itself, because in the region where this integral converge, where the sum converge, the polynomials are oscillatory. So what's positive is the coefficient of the Lejeune polynomials, not the amplitude. That's what we want to use. So if you take this, if you evaluate this sum rule, so on the left, you just do the contour integral of this amplitude. And you get some simple function that I'm going to write here. The function you get is this. So there's something from gravity, and then there's a series of higher derivative terms. So it's a series in T. So you get an equation that's valid for any momentum transfer that relates low energy physics to this average bracket here. Just means sum over AV states with different mass, different spin, with positive coefficients. And the average depends on the momentum transfer.
Sorry, Simon. If you were working with massive particles, could you extend T beyond the physical domain? Could you take T to be positive but less than 4m squared in your relations?
Well, if they're identical, T equals 0 is allowed. Yeah, I mean, if they're not identical, there will be some lower value, I believe.
Sorry, so but if your scattering particles were massive, could you take T to be positive? Let's say they are all massive and identical. Could you take T? Would your dispersion?
Yeah. So yeah. The rule here is the rule is that you have to look at the. So we think of the allowed values of T or whatever is the physical region when S is bigger than m squared. So we think about the energy is S, and you ask what are the physical momentum transfer, and that's the region.
And why aren't you allowed to extend T a little bit beyond that to, let's say, positive values rather than negative values of T?
Oh, this is very bad, because if you don't have a mass, it's basically the Lejeune polynomials, they go from oscillatory to exponential. The sum is not going to converge.
Right, but I thought
you can see here that it cannot converge because the sum has to diverge when you approach to go to 0. With gravity, you're not going to be able to cross 0.
Right, but I thought, for instance, in the derivation of the Froissart bound, you allow for that.
Yeah, in the derivation of Froissart bound, you use the regions between T 0 and 4m squared.
Right. So are you allowed to use that region?
If you don't have gravity, probably. With gravity,
yes,
no.
Just for massive particle scattering. Massive field theory scattering.
Yeah, and massive field theory, I think you will be able to.
Okay, thank you.
Yeah, but yeah, basically because of the same argument by Martin that mean, naively, this sum diverge, but you can show that actually it converge up to the pion mass. So
yeah, simply because the rho j's themselves decay exponentially faster than this growth. Right?
No, yeah, the quotient here, yeah, exactly. The quotient will have some exponential growth set by the pion mass. Yeah, yeah, thank you. Yeah, that's a good point. Yeah. So yeah, the standard, basically standard arguments about the range apply. So let's see how we use this equation. So well, first of all, there's infinitely many unknowns on the left. So if gravity was if there was not gravity, then we could easily single out individual terms here by expanding around the forward limit. And this is what has been traditionally done in this business. Expand around zero momentum transfer. And that's why people talk about momentum transfer. And then clearly you get a sum rule for this first coefficient in terms of, if you set momentum transfer to 0 here, you get some simple power of 1/4. And it's a positive sum. So clearly you wrote the low energy coefficient as a positive sum in the UV, and you can derive interesting sign constraints on this. And you can extend this. I will not go that direction. And directly talk about the gravitational case. Now,
so I'm sorry to constantly interrupt you, Simon, but
no, it's fine. That's the point of these talks.
Okay, great. You know, if I understand right, you have a clear definition of this capital M, because effectively your field theory at low energies is assumed to be classical, so there are no loops there, and so then capital M is the first sort of non-analyticity apart from some specified poles.
Yeah, correct. Yeah.
Now, if you went a little bit away from this limit, so you allowed for some low energy loops, then would the notion of capital M become fuzzy?
Well, no. Well, yes and no. Well, mathematically, you can still play this game and split the dispersion ratio in the part above a cutoff and below the cutoff. You can always do that even if your cutoff means nothing physically.
Right. But I would.
But if your AFT is weakly, if your AFT becomes strongly coupled near the cutoff, then like you're not going to be able to actually compute anything. So in practice, you will need your AFT to stay weakly coupled below the cutoff. Well, at least near the cutoff. I mean, it could be like, QCD as look like partons at high energies, and you could use a weakly coupled parton picture even though it's strongly coupled in IR, but you have to be in a region where things along this arc are weakly coupled. Yeah, if it gets strongly coupled around the cutoff, then this is one way that effective theories sometimes break down, because it becomes strongly coupled with their cutoff. In this situation, our definition don't help you give a precise meaning to what the cutoff means.
Okay, thank you.
But some other times you have cutoff because you have very often, actually in nature, that's what happens. The new physics is weakly coupled. And in that case, the cutoff is very clear as the mass of the new states.
Right. Effectively, when the physics up to the cutoff is tree level, I understand exactly what you're saying.
Yeah. So yeah.
Okay. Thank you.
Mm-hmm. No, but you could imagine having some strongly coupled sector that's coupled to a sector that's itself weakly coupled, and this also applies there.
Okay. Yes.
But yeah. But the things with scattering have to stay weakly coupled. That's the idea. And gravitational effects are of this type because gravity is free theory in IR. So this business about loops is especially irrelevant for gravity.
But it would be relevant for M theory. Suppose you were interested in M theory, then the cutoff would be like the Planck scale. There's no other scale in the middle, so there would be no sharp capital M. Right?
Yeah. You would have to, in practice, you would have to use M that's lower than your cutoff and hope that somehow you're still able to probe to reach. But yeah, good point.
Okay, thank you.
So let's see how we actually use it. So the basic issue with gravity is that you have infinitely many things on the left, and like to bound anything, we like to zoom into one thing. And here's a strategy that we explained we pursued in the paper last spring. Like you can try various things, like, well, simple things don't work. Like you cannot just like pretend this pole is not there, or you cannot like subtract it, because if you subtract it, dispersion relations does not hold anymore because gravity goes too fast with energy. like the thing that's special about gravity is that even already at 3 level, it violates these bounds. So gravity requires the UV completion already at 3 level. So you can't just subtract it. And so what we propose is the following. The idea is that when you start looking at these sum rules, you discover that there are many ways to measure each coefficient. Like if you look at the higher subtracted sum rule, so that's a 4 subtraction sum rule. You find that the first thing you obtain on the left is this coefficient G4 that was already there. And that's easy to understand. It's because that's just crossing symmetry in the infrared. In the effective theory, you have 2 different amplitude, like 2 different terms you could trigger on, like energy the 4 or energy squared T square. And by crossing symmetry, these 2 terms need to have the same coefficient. So basically the idea is to use this higher subtracted sum rule, which don't have a graviton pole, feed them back in to eliminate all of these terms. And we can do that. We show the explicit formula. And after you do that, you have an improved sum rule where you just have finitely many couplings on the left. You have infinitely many sum rules. So that this U here is T. You have infinitely many sum rules which probe the same 3 things, and these 3 things are all the couplings which are not probed by which go slower than 4 powers of s, which is finitely many of these things. So we have these improved sum rules, and it's some specific average that I'm going to write down. And then once you've solved this problem that you measure only finitely many couplings, then the idea is to try to make combinations of these sum rules that gives you positive average on the right hand side. Then so mathematically we construct wave function such that when you integrate against this sum rule, so infinitely many sum rules for any value of momentum transfer that's physical, we integrate them, and if you can construct a functional such that the thing you average is positive for all the mass above the cutoff and all spins, well, then it gives you an inequality that the left-hand side has to satisfy. So that's how we get bounds on no energies. Take positive combinations of these things. So, and amazingly, positive combination of this thing exists. so they're kind of cool functions. They have the following among properties. They satisfy the following. So they have compact support in P, that was by construction. They vanish at the decay at large P, but there's also have to be positive in impact parameter, otherwise they wouldn't be, the action wouldn't be positive. So it's kind of cool, right? You have to find functions of positive in impact parameter space with compact support in P. And like, there's a theory, such function exists. Like in one dimension, well, in one dimension there's a theory, like for example, this integral. You can integrate P, if you just integrate momentum over cosine, you're going to get a cosine which oscillates and not positive. But miraculously, if you multiply it by 1 minus P, you end up with an integral that's 1 minus cos, that is positive. So this function exists, and actually we don't know a general theory of this function in general dimension. So in practice, what we do, we just make a polynomial ansatz and use linear programming to like find combinations that are positive. And a computer can find this combination for us. So it'd be very nice to understand this better, but like we know these things exist and can explore them. So using, once you have this polynomial, I don't write one, they're really ugly, the ones that come out from the numerics. You prove bounds. Okay, so in the bounds here, yeah.
Could you say again what the rationale for these 2 properties? Boundedness in compact support in P and the positivity in B. I guess the positivity in B is because of unitarity. I mean, you want to preserve this.
Yeah. The reason we now want them to be positive in B is that like the mechanism by which we prove bounds is that we want to make averages that are positive in the UV.
Okay. Yeah.
And any average that's positive in the UV gives you an inequality on the things on the left.
Okay.
So it's for the application.
Yeah, okay.
For application, we want that.
And the compact support in P because...
yeah, that's because our sum rules are not valid otherwise.
Right. Right. Okay. Yes. Thank you.
Yeah. So yeah, using these, you find inequalities that involve this G3, the gravity, and this other coupling. So just to remind you, G2 was the quotient of del phi, the 4th derivative thing. G3 was the 6th derivative interaction. That's like STU. And it's basically a two-sided bound on STU for a given, like it's two-sided for a given value of the other couplings. Basically, there's a dimensionless ratio with that is there. And yeah, so we get bound of this shape. So this is splitted in different dimension. One thing which is kind of an important qualitative point is that for long, like without gravity, there was this important statement that G2 is positive that people use a lot in the past to rule out some theories. And an interesting fact is that when you turn on gravity, so without gravity, like you will have a cone that starts from the origin, but gravity allows some negativity here. That has a simple interpretation. Like gravity gives you like time delays, so you can kind of compensate by having contact interaction that give you a little bit of time advance. So that's it's not so surprising that negative G2 is allowed when you have gravity. But this physics is important. If you don't include it, like you can look at things like the photon scattering below the electron mass and apply similar arguments, and you find that you have some negative coefficients that when you for the analog of Euler-Heisenberg, when you have gravitons on the outside. Anyway, you can run into paradoxes if you don't include the fact that you get a 3-level graviton allows for some negativity. But yeah, that's a story. Let me elaborate a bit on this picture. So the shape of this region is generally some cone. It's open to the right in this particular scalar theory because you could set gravity to 0. Like the axis here is basically the strength of the scalar self interaction divided by gravity. So of course you can set gravity to 0 and still have an interacting scalar. So it's open to the right. But it's basically like a simple cone, which means that there's a linear relation between G3 and G2. So let's discuss this limit where we shut down gravity a little bit more. So if we shut down gravity, then yeah, you can have interactions, and then you get two-sided bounds that just involve the non-gravitational interactions. Okay? Let me elaborate a bit on these two-sided bounds. So when you not have gravity, the analysis is much simpler. And that's actually what we did in a paper last fall. Because then you can just expand around forward limits. And you get averages that are like this one that I mentioned already for the leading interactions. When you look at subleading interactions, it works kind of an interesting way. So you write down this sum rule, and you get, well, you get two kind of things. You get dependence on the spin of the heavy particles, because you have to take derivative of Legendre polynomials. To probe this G3, we have to take a derivative around the forward limit. And when you look at these sum rules, well, it's obvious that you have some upper bound. Like you're averaging over states that are above the cutoff, and therefore G3 clearly cannot exceed 3 over, well, M6 is less than 1 over M6 is less than 1 over M4 times the cutoff. So clearly you get, it's very trivial to get upper bounds in these things. But when you look at this formula, it looks hard to get a lower bound, because you have to bound somehow the spin of the heavy states, but heavy states don't have bounded spins. And I think this problem remained open for many years, but there's a solution that came from also from us and a different group last fall, which is that when you really use infrared crossing symmetry, as I mentioned, there are two ways to measure the next coupling, the next order coupling. G4, there was two ways of measuring it. So if you take the difference, you get something that's a pure constraint on the heavy states. It's really constrained. It's not really a constraint on UV. It's really constrained in the way that UV couples to IR. But yeah, this constraint, if you stare at this constraint, you have to, one of the terms, you have to take 2 derivatives on the forward limit, so you get spin to the 4. And you stare at this constraint, it's clear that it prevents states with I spin from contributing too much. And you can manipulate this constraint and Cauchy-Schwarz blah, blah, to really show the following, that you can bound expectation values of the spin. And so every time you insert this combination, J square over M square, which is like the impact parameter, you have to pay the price of the cutoff. And that's a remarkable fact. And that really underlies why these sum rules work. It's, as far as these sum rules care, you can treat all of the states are small. That doesn't mean that big of states don't exist, like black holes, long strings, and so on. They can exist. But the point is that they never contribute significantly. The crossing symmetry forces the coefficient to be small enough such that they never dominate these sum rules. These sum rules are dominated basically because of the inverse powers of energy, and the subtract goes by the subtractions. The sum rules are always dominated by stuff just above the cutoff, which we imagine is below the Planck scale. And error crossing prevents big states from contributing too much. So basically, you can effectively bound the spin, and that's why we have two-sided bounds in the end of the day.
And this last this statement about B of order 1 over the cutoff dominating, is that true also with gravity?
Yes. Yes, because crossing symmetry at low energy is valid even with gravity.
I see. Even though this.
The simple argument here was using forward limit sum rules, so we can question whether it really it works in general. But yeah, we see the same phenomenon with the more clever sum rules here with compact support in B.
Yeah, I was going to ask about the physical point that we discussed earlier, that in gravity you expect the impact parameter to grow with S for some scattering regimes. Yeah,
but basically it's basically this factor of 1 over M4, which is making you not care about this high energy physics.
Okay.
So physics above the Planck scale can only give you a very small effect. It's a non-trivial result. I mean, it's confused people for a long time. But if you think about, for this particular problem of constraining low energy effective theories, a low energy, the EFT doesn't care about black hole physics. Basically, that's what we're seeing.
Sorry, I'll just ask again, just to make sure. In the Regge limit, again, Veneziano explained in the strings meeting that amplitudes are dominated by things very far away at very high energy.
Yeah, you can have fixed angle scattering from classical effects outside the.
And Regge as well, right?
Yeah.
Okay. That looks like impact parameters that are growing very rapidly.
Yeah, but this physics occur at values of M, which are going to be killed by this.
Okay.
This factor is just is making all this physics irrelevant.
Okay, thank you.
So what is this factor? Where is this factor coming from?
Ultimately, it's because we have to do 2 subtractions. No, the things we can bound involve 2 subtractions, and that's it. Yeah. So that's the physics I wanted to cover, and here I just want to say, just want to drive home the message, is that these forward limits bound are very well understood, and yes, for example, they have a simple take-home message, is that causality implies EFT power counting, because you can get bounds like this, 2-sided bounds on every single term in your effective action. But it's 1-sided on the first coefficient, and then it's 2-sided. So this G tilde are ratios like GK over G2 with some power of the mass, make it dimensionless. So you get 2-sided bounds on every coupling, and these bounds are basically compatible with the geometric series that you would think.
And it's 1-sided on the first coupling because that's positive.
Exactly. The only thing we know about first coupling is it's a lower bound.
But wouldn't effective field theory reasoning say that should also be bounded from above?
Well, it should be, it's bounded above by some strong coupling arguments, but it's hard to make these bounds sharp, as we discussed, because the cutoff is not sharply defined in that case. But yeah, there's of course always a parametric bound that G2 has to be less than 1 over M4 in order for loops that the 2 loops remain under control within the EFT, and you can put some factor of pi square in there.
And in the situation where everything's classical at up to scale M, in that situation, can you find sharp bounds on G2 as well? where there's a clear meaning for scale M.
No, it's only a sharp lower bound.
Okay, thank you.
Sorry, Simon. Even when the effective field theory is weakly coupled, you could have the partial wave amplitudes getting constrained by the non-perturbative bound, right? Or not?
Yeah, and exactly, and this gives you a parametric bound of this type.
Right. But you said
but
that.
But then the problem is that these are not sharp bounds, because I mean, but the fact that partial waves remain less than 1 is a sharp statement. But when the partial waves get close to 1, it means that loops are very important, and you don't really know how to compute anything.
So why?
So what are you bounding exactly?
Loops are very important. I mean, you could still imagine. Why does that mean loops are very important? Because these partial wave amplitudes are at very high scale, right? You are looking at some Planck scale cut and so on.
No.
You could still have weakly coupled effective field theory.
Okay, I see what you mean. Yeah. So there's yes. So if you think about energies and there's a cutoff here, and then there's this Planck scale here, and you can look at the partial waves. Yeah, you can imagine a situation where the partial waves stay small up to the Planck scale. That's a situation like this that you have in mind. In this case, it's covered by our bounds. If it's weakly coupled to the EFT, it's covered by our bounds. But you can ask, like, is there more information you can get from the fact that it stays less than 1 even at the Planck scale? And probably yes. Yeah. We have not used that information here. So these bounds are not may not be optimal.
Thanks.
We just know that they're correct.
Okay. Thanks.
Yeah. Thanks for this point. We have not used this physics. Okay, and the other thing I should say is that these forward limit bounds, which are now well understood, and actually there was a nice paper in the spring about the EFT hadron reproducing these numbers. So there's actually a lot of analytic understanding there. These bounds, we can, when we look at our more fancy approach, which involve integral over momentum, that really focus things to small impact parameter, we reproduce the exact same plots. So either from forward limits and from small impact parameters. So the approach are completely equivalent at the end of the day. But just to recap, the small impact parameter approach has some advantages. And the first of them is that, well, it seamlessly deals with the graviton pole. So we add gravity, and it's like a small gem. It doesn't change the method. And the other thing is that, as I stressed, it's much easier to justify physically, because you don't run into question about, try to justify that m over s squared go to 0 and estimating Fourier transform, blah, blah. We just sidestep those functions and just use the fact that things are bounded and fixed impact parameters. So they're much easier to justify. So I think these results are really robust for this reason. So I'm pretty much done explaining the physics. So what I had prepared here is some slides about what we did in CFT. I'm not sure it makes sense to rush into these slides. I think if people want, we could talk about some highlights after. But basically, yeah, maybe if I can say just a word or two. So that's what well, actually, David Simmons-Duffin gave a beautiful talk on Monday on this. But the basic setup is that we want to study a large N theory with a large higher spin gap. And the basic setup is that our tool is the orbital product expansion of the CFT, 4-point correlation function. And this OP has a following structure. There's the identity, it has like double trace operators, and then it has like single trace and AAV things. And the basic goal of constraining, well, what you have to do to constrain the effective theory in ADS is to get some relation between the interesting physics lies in this like single trace, so like graviton exchange and so on. And the goal is to relate this light physics to AV physics. And the problem is that the reason you cannot really do it with numerical bootstrap tools is that you have to kill, this is like noise that you have to kill. So the new development basically is that we have a simple tool, this dispersive sum rules in the CFT, that kill those things so that you can focus on the interesting physics on the right. And the mechanism by which we kill this is to have some rules that involve a double commutator. The same sort of thing that occurs in chaos exponents. And the way we obtain this sum rule is actually what I like about this. I'm just going to sketch this argument enough that you can see that it's almost a flat space argument. it's like the crossing argument, crossing symmetry argument run again. So you take this commutator and you take it close to the light cone, and that's where it's like you take the statement that commutators vanish space-like. You take the statement close to the light cone, and actually you integrate it over parallel light rays. Like this is like as close as you can get to the light cone. Any point here is space-like from point here. And this integrated operator have the cool property that they annihilate the vacuum. So this commutator you can write as like when you integrate, you can turn this to a commutator. So this identity gives you a double commutator minus a double commutator with 1 and 3 swapped. So it gives you a projection of the crossing equation, which only involve the d disk on each channel. So you have d disk in the S channel equal d disk in the T channel. And that kills all this junk and allows you to focus on that. That's the basic trick. But it's actually the same. This commutator square is a thing that reduces the flat space limit to the imaginary part of the amplitude. There's actually some quite pretty discussion of ADS cutting rules by Meltzer recently. And for this integral to work, it has to be well defined. But in CFT, you have rigorous bounds on correlator. You know when they're bounded, so you can rigorously know when this integral converge. And the basic lesson here is that you need more than one subtractions. Okay.
So you're working in the CFT Regé kind of limit, right?
Yeah. Okay, yeah. Since you ask, I'm gonna finish the talk with a plot. Yeah. So in CFT, as you stressed in your paper last spring, the same problem that I mentioned in the beginning also exists. There's a space-like region. Also the Rindler kinematics, where 1 and 3 are space-like. This is the region where this crossing equation is valid. 1 and 3 commute. But the region that you normally use to focus onto a bulk point requires you to be, in order to be able to causally focus, you need this point to be in the future of 1 and 3 to be time-like separated. So it's the same feature as in flat space, right? The region where you can localize in the bulk does not overlap with the region you have control over. And we do all of our calculation in a space-like region. We never exit the Rindler wedge. And I'm going to tell you how we probe space-like scattering from the Rindler wedge. It's hard to probe scattering from the Rindler wedge. Basically, right, you cannot causally focus. So all you see from this blue screen here is a smeared image. It's completely smeared. Like the bulk to boundary propagator in this region, they completely spread over the ADS radius. It's a very unfocused image. But still, we unscrambled it in the following way. The trick is the following. I mean, yeah, the trick. Okay, we consider. So we have to integrate over this point with some weight. Okay, we're gonna skip this detail here. And we have to integrate over this point and just shoot the basic picture here. And the basic idea is to integrate over something that's very oscillatory. So this is a point on the boundary, and we integrate it against some functional that's supported inside the Rindler wedge, but is highly oscillatory. And there's a nice thing about the symmetry, the way symmetry works. The same symmetry group acts on the boundary and in the bulk. So because we're in the rigid limit, the word scattering is localizes to this transverse hyperbolic space. That's HD-1 already. But the isometries of this space, the same isometries act in the bulk and in the boundary. So by injecting a large momentum on the boundary, we can inject a large momentum in the bulk. That's what we use to localize. Okay, and mathematically, what we show is that so the way so this is like this harmonic function on the boundary. If you integrate a heavy block and we take a block that's exchanged in that horizontal channel, exchange space-like. If you integrate this oscillatory function against a block, what you get is the same harmonic function, but now of bulk quantum number. So this cos beta is this bulk quantum number. And the bulk impact parameter is really defined. It's just a kinematic thing. Is log of delta minus j. It is defined from the quantum numbers of the states. In the same way that in the same way that in flat space, the impact parameter is related to the spin and mass. You can do something in the bulk. So we get large momentum in the bulk in that way. And then once you have large momentum, it's easy to localize to small impact parameters. Physically, the way it works is really kind of cool. The way it works, when you apply it to an amplitude, the way this works is that we're thinking about exchanging states horizontally. These points are like defined as causal diamonds, so these are space-like, so it's natural to exchange in that channel. What happens is that when we integrate over these very oscillatory functions, we create a saddle point that is complex, and on this complex saddle point, time and space are exchanged. So that's why we resolve the bulk, because if you exchange space and time in this picture, now you have bulk point. Now we can causally focus on the point in the middle. Okay? That's a trick. That's the trick. So in other words, we don't like this is bulk point singularity. We want to probe it. We don't probe it just by going there, because then we will lose control over our integrals. We probe it by indirectly creating a saddle point that happens to approach it.
Sorry, Simon, I mean, going to that region and doing it later, should you not have encountered the same problems? Like now, because you did this and you found a complex saddle, and the previous issue going to this time-like region was somehow the crossing was not going to be valid, right? Over there.
Yeah.
So
yeah, but
why
now
doesn't that bite you again?
Yeah. Well, we start by basically integrating. We're integrating out a valid crossing equation times oscillatory function. So clearly the answer is it's an absolutely convergent integral that has to be valid. And but you can see that there are limits to this, and the limits come, the limitation come because the saddle point only works when you act on every state with delta bigger than the momentum. So you see this restriction that so at the end of the day, the way we set it up, so there's a momentum nu that you inject into this transform. It has to be less than the dimension of the operator you act on. And the way we achieve this is by having this gap. We act only on EV operators, and by insisting that we stay in this physical regime. So it's very important that we only we land on the physical region. So that's how we achieve it. But yeah, we can this. So this is for the saddle point to work. So let's put it differently. There was nothing wrong before with just approaching this region, but the problem is that you didn't know when it breaks down. Now we can tell you exactly when it breaks down. The connection with flat space physics breaks down when the momentum exceeds the dimension of the operator you act on. So that's how we can get sharp bounds. Yeah. So the fact that these regions are connected, so this seems to generalize a relation that was noticed in your paper last spring. So this is so nice to better understand. But I think that this general saddle point argument seems quite general. Okay, I'm basically done. So I also mentioned that the saddle point it has a nice physical interpretation that matched with something that my student Lee has recently worked out for spinning 3-point coupling. So I think it's very clear that you can do the same analysis works in the spinning case. And yeah, on the saddle point, you reproduce exactly the flat space sum roots. So we constructed CFT sum rules that have exactly the flat space limit you expect. And we can check actually that these sum rules are already positive. So in other words, to conclude, we made this machine that takes an S matrix sum rule that's labeled by number of subtractions and a momentum transfer that is in some compact support range. And we have this machine that just substitutes the momentum to this ADS momentum, and that gives you a CFT sum rule. And positive sum rules map to positive sum rules. So basically all the results we probe in flat space just carry over to ADS theories with a large, CFTs with a large gap. Okay, so it's a machine to convert positive EFT bounds, these two spaces. Okay, so I wanted to make quick comments about what the distinction between EFT and so on, but yeah, I think I will conclude here. So in terms of physics, I think the main there's a kind of cool message is that causality implies two-sided bounds generically on EFT coefficients, which is remarkable. We often said, when I started doing this analysis, I said, well, I want to, in the space of EFTs, I want to study EFTs that are causal. And now I realize that this phrase does not make sense. It's like a pleonasm. If you study a causal whatever, it's going to look like an EFT in some sense. You don't have to add in EFT power counting. It comes out. So yeah, and I think one interesting direction we're going with this is limits on causal modification of GR. It's clear that this, because GR is spin 2 and requires UV completion in 3 level, it's clear that the most interesting limits from this method are modifications to GR. We're playing with that, but there's really a lot to explore. Like dimension 6 operators in the standard model, loop effects. We find interesting kinks. One thing that's interesting with sharp bounds is when people analyze them, they discover, for example, that the Ising model was a kink. So sometimes you find interesting places, interesting theories which saturate bounds. And like this question here: do we have any interesting theories which saturate these bounds? Then if that's the case, then you can start solving these theories. There was a question about using the upper bound on partial waves. We haven't used that yet. Other people are thinking about this. We told you that flat space physics, any flat space sum rule can be uplifted to a CFT sum rule, which is cool, but it's also a bit depressing because you might think that theories in ADS should be more constrained than flat space theories. So we have yet to construct a single sum rule in ADS with a large gap that is more constraining than the flat space. That's an important problem. Yeah, I think we're just scratching the surface basically with these causality constraints. So thank you.
Thank you very much, Simon, for a very nice talk.
Good. Could I ask one quick thing?
Oh yeah.
Maybe you said this, but in the case of flat space, you talked about how most straightforwardly you can prove crossing it's when two of the operators are space-like separated. Yeah. But the phenomenon continues when they're time-like separated, and that leads to crossing of S matrices because of larger domain of analyticity and so on.
Yeah, exactly. So maybe if I want to add one thing about this is that it feels like the sort of argument that we did in CFT could be done in flat space. Let me say it here. So I mean that would be an alternative to this whole line of approach, but it sounds like maybe the heuristic picture, it would be very nice to see if that works. Maybe it doesn't work, but the idea would be you start from this blue screen, which is space-like, and you do some like clever Fourier transform, and that's going to be bounded and controlled, but it's going to have a saddle point that's deep inside the LSZ region. So it could be that our CFT proof kind of works directly in flat space also.
Right. This was going to be what I was going to ask. But now in CFT, you use the chaos bound or the quantum chaos bound.
Yeah, the fact that correlators are bounded. Yeah, not just the fact that they grow less than the chaos bound.
Is there an analog of that statement for this space-like kinematics in flat space?
Yeah, I think it's. I think you can prove this. The proof using like Cauchy-Schwarz thing about double commutator being bounded by the disconnected thing. I think it holds in flat space too. And yeah, this is discussed by I think the paper by Meltzer on dispersion relations and CFT discusses that. Yeah.
Okay, and just turning this around. So when you explain this, that what you did in ADS could have been done in flat space.
Maybe, yeah, it is conjectural, yeah.
Right. But sort of turning around, you know, if you take the lesson from flat space to ADS, that would suggest that the region of in which crossing applies is larger than where it has the right to apply.
Yeah.
That it actually applies in some time like region.
Yeah, I have one thing to say about this. Yeah, you ask excellent questions. Yeah, I have something to say about this. Is that in this context of CFT, there's something really cool that happens. Is that explain that you get a sharp saddle point in some range, but you still get a well-defined result outside that range. It just doesn't clearly as a flat space interpretation, but like you can like in CFT we could relax this and get more general sum rules that we don't know yet how to interpret in flat space. Like you break the saddle point, but you can still you still get the well-defined result. So in other words, there's a space of CFT test function. And the space of CFT test functions we define in appendix on our last papers is it's actually some analysts say that it has to decay. The functions have to decay exponentially with nu. There's some constraint on the space of test functions, but it's strictly bigger than compact support and momentum. So we use things that are all the bounds we proved so far use this small set of test functions. The bigger set takes you away from things that have a simple flat space limit, but they exist. I don't know what they do. I don't know if that relates to your question.
Thank you.
Do you have any more questions for Simon? Okay, if not, let's thank Simon again for a really wonderful talk.